Okay, for some statements, like this one up above, we can define them for positive integer values of n. So we started with 1, went up to our first n terms, and we could write that proposition as p sub n. And then we can prove it using mathematical induction. So let's look at the process of induction. So the way that principle of mathematical induction works is that we start with a specific example. So inductive logic, specific example. So we show that PA is true, and then whenever P sub K is true, P sub K plus 1. So 2 consecutive propositions are always true. So the previous proposition implies that the next one is true. The way that this works in practice is that we'll make some sort of statement. We'll show it's true for a specific example. It's usually n equals 1, but not always. And then we state that our assumption P sub K is true. So we're going to use words for this. Showing it's true, generally that's algebra. And then definitely, almost definitely, we'll be using algebra to prove that the P sub K plus 1 statement is true using this assumed to be true statement. So this is algebra, and the key here is that we have to use P sub K. And then we write our conclusion statement, and that happens in words. So let's look at a specific example. Let's formulate a proposition defined for positive integer values that give the sum of these terms. So we're looking at the sum of rationals formed in this pattern. So let's look at n equals 1. For n equals 1, we get 1/2. For n equals 2, we're going to get 1/2 plus 1/6. Sorry, this is not equals. All right, if I work that out, I'm going to get 4/6, which is the same as 2/3. Now let's go for n equals 3. I'll take this, and I'm going to add 1 over 3 times 4, so 1 over 12. All right, multiply top bottom by 4. I'm going to get 9 over 12, which reduces to 3/4. So I'm seeing enough of a pattern right now that my assumption for P sub n is that if I take 1 over 1 times 2 plus 1 over 2 times 3 plus and sum all the way until 1 over n times n plus 1, that sum is going to result to n over n plus 1, because that's what I was seeing in these examples. We know it's true for n equals 1. So here's my P sub n statement. That's what I did first. So I'm going to come back and number this. This was number 1. Number 2, I'm going to show that P sub 1 is true. So P sub 1 is 1 over 1 times 2. Does that equal 1 over 1 plus 1? Sorry. So we get that 1/2 equals 1/2. Therefore, P sub 1 is true. We want to make sure that we write out that P sub 1 is true. Step 3 says to state that P sub K is true. So, and it's stating our assumption that is true. So I'm going to use the word assume. P sub K is true. And furthermore, I'm going to write out what that implies. So that implies that P sub K is 1 over 1 times 2 plus 1 over 2 times 3 plus, so now I'm looking at P sub K, 1 over K times K plus 1 is equal to K over K plus 1. So I'm assuming this is true. Step 4, we want to show P sub K plus 1 is true. So that is p sub k plus 1 will be that 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over k times k plus 1 plus 1 over k plus 1 times k plus 2. So I'm going to the k plus 1 term. So I'm going to the next term. So k plus 1 plus 1 is k plus 2. I want to show that that's equal to k plus 1 over k plus 2. Again, k plus 1 plus 1. So to show that this is true, using my assumption, I'm going to, again, show. So I'm going to work only with my left-hand side and hope that it equals the right-hand side. So the left-hand side, my 1 times 2 plus 1 over 2 times 3 plus 1 over k times k plus 1 plus 1 over k plus 1 times k plus 2. This equals, well, I'm going to use my assumption. So this part here is equal to this from my assumption. So I'm going to substitute for this with this. So I'll get k over k plus 1 plus 1 over k plus 1 times k plus 2. So now I'm going to create a common denominator. K times k plus 2 plus 1 all over k plus 1 times k plus 2. I'll get k squared plus 2k plus 1 over k plus 1 times k plus 2. Notice this factors as k plus 1 squared over k plus 1 times k plus 2. When I simplify, I'm left with k plus 1 over k plus 2. So I've shown that k plus 1 is true when I use p sub k. So my fifth step would be to write out my sentence finishing the proof. So since p sub k plus 1 was true, and p sub 1 was also true, then by mathematical induction, p sub n is true for all n greater than or equal. In this case, I'll say for all n elements of natural. So I'm actually going to write out those words. So since p sub k plus 1 is true, and p sub 1 is true, by induction, p sub n is true for n element of natural numbers. So in this case, I picked what fit for my situation, which was n element of naturals. So you'll pick what fits your given initial condition.